So we know the continental plates are moving, not just the continents, but the ocean floor as well. So we have plate tectonics, sections of the Earth's surface going in motion. And so we got this convection that goes on, and we're rifting, we're cracking the surface. The ocean floor is moving one way, the ocean floor is moving the other way, and so you're separating. So the youngest rocks are found right along that continental rift in there, the oceanic rift, and then they're a little bit older further away, and the farther away you are, the older the rocks are, because you're pulling things away. Okay, so you're going backwards in time. Now, this is an interesting sort of thing that we discover. When the rocks are molten, okay, these are basaltic type rocks coming from down deep. And basaltic type rocks have tiny little iron bits in them. And so what's happening is that these basaltic rocks coming up, when they solidify, they actually tend to pick up just a tiny little bit of that magnetic field. This is how you get lodestones, in fact, is you cool a rock in the presence of a magnetic field. If it's got iron in it, it's going to be slightly magnetic. There's something called the Curie temperature. That's the highest temperature something can have and still be magnetic. And so the rocks, when they're molten, are way over the Curie temperature. They cool, and now they're going to be below the Curie temperature. They pick up the magnetic field the Earth has at the time. Well, what you notice is all these young rocks are going to have the same magnetic field orientation as Earth in here. Well, what we discovered, though, is that as the plates separate, all the new rocks are lining up with the Earth's magnetic field. But if we look out there today, we find the rocks right near the crust, the very young rocks that have just formed are in fact lined up with the Earth's magnetic field, but off to the side, the rocks are actually reversed. So they have magnetic fields pointed the other way. And then the rocks here are lined up with the Earth's magnetic field. The rocks there are pointed the other way, and the rocks there are lined up with the Earth's magnetic field. And so what does this tell us? Well, the rocks are always going to line up with the Earth's magnetic field. If they're lined up the other way, that means the Earth's magnetic field had to have been the other direction at that time. So this suggests, therefore, that the Earth's magnetic field actually flips. So on occasion, the Earth's magnetic field reverses. Okay, so what would that mean? Okay, so Earth's magnetic field reverses. And again, we can actually work backwards. We call this paleomagnetism. We can work backwards looking at how the magnetic field is oriented. And so the magnetic field is always going to be oriented the way the magnetic field of the Earth is at the time. So we can work backwards and figure out how frequently the magnetic field reverses. Okay. And what we find is that on average, the Earth's magnetic field reverses every couple 100,000 years. You know, maybe a 250,000 years or so, the magnetic field reverses. Okay, that's on average. Now, sometimes it goes a little bit longer, sometimes a little bit less. The last magnetic field reversal was actually 780,000 years ago, so that's a lot longer than normal. That means we're actually quite a bit overdue for a magnetic field reversal. Now, that turns out to be interesting because Earth's magnetic field is part of what protects us from particles of radiation from the sun and from deep space. So when Earth's magnetic field tends to degrade like this, that's going to have a huge impact. Now, nobody really knows when the Earth's magnetic field reverses whether it does it kind of quickly or takes a long time to do it. The sun's magnetic field also reverses about every 11 years, and it is pretty strong for a while, and then over a short period of time, it kind of drops down to zero. It's close to zero for a little while, and then it rebuilds. Does Earth's magnetic field do that? If so, that means for a period of time, we're not protected against all these stray radiation from space. On the other hand, does it happen quickly? Okay, does it happen slowly? Or does it just become chaotic with the magnetic field all which ways until it finally settles down in a new way? Geologically, we know that it happens pretty quickly. Pretty quickly geologically, because these layers of rock do not have great spaces between them, in which the magnetic field, is chaotic or something. Geologic time, though, is pretty long. Okay, so that means this could happen, geologically very quickly, but that might be a very long time by human standards. Well, we'll point out though that from about 120 million years ago until 83 million years ago, so that's a period of about 37 million years, the magnetic field did not reverse. So even though it reverses on average every couple 100,000 years or so, there was a period of time here for an extended period of time it did not reverse. So that means that there's not really anything that says it's about to happen, even though we're overdue. By average, we're overdue. There have been times have gone even longer. So there's nothing really that's saying right now it's just about to reverse. Okay. So what causes it to reverse? The standard idea is it's due to chaotic turbulence in the Earth's outer core. But the true nature of these reversals is not really fully understood. And so that means that we don't really know for sure what causes them, which also means we don't really know for sure, that we're not about to have one, or that the signs are, out there, are telling us much of anything. It is believed, possibly, that rather than the magnetic field simply dropping down to zero and then reforming, if it's due to turbulence in the outer core, the magnetic field could get very bizarre and weird instead. Now, that's good and bad. I mean, to still be a magnetic field there to protect us somewhat against particles from space, but it would mean it's not a nice, neat sort of orientation. That would mean that this would be incomplete protection from space radiation, and it would also mean that this is not going to be something that's going to be very helpful for our satellites, which are orbiting in the midst of all that. So we really don't want to have a magnetic field reversal in a technological society such as we have right now. Well, we can work backwards in time for thousands of years and find out what the Earth's magnetic field is doing. Right now, the Earth's magnetic field, it has been gradually getting weaker, and it's been getting weaker for about the last couple thousand years. Now, that doesn't mean that we're about to go into reversal, because it has been much weaker than that. It was much, much weaker than it is right now. About 7,000 years ago, and it was also quite a bit weaker about almost 11,000 years ago. From 11,000 years ago up until about almost 8,000 years ago, it was gradually increasing in strength to about what it is now. Then it started dropping again, and then it increase in strength until about 2,500 years ago, and then it kind of plateaued for a little bit, and for the last couple of thousand years it's been steadily dropping. So we've lived here, most of civilization has developed during a period of time in which the Earth's magnetic field was actually quite a bit stronger than normal. That actually turns out to protect us a little bit more from radiation from space. So don't know if that's really why we've developed it during this period of time or not, but it is nice to know that that's happened. Okay, so what does this tell us? Not a whole lot. Okay, it just tells us the magnetic field has been gradually decreasing in strength. We also know from previous lecture it's been shifting where the poles are a little bit. That could be due to this turbulence in the outer core. This could be precursor to the magnetic field reversal, or it could be just a cycle that's going to turn around and get stronger again. We don't really know.